Welcome. So the topic we'll be discussing in this lecture is spanning trees. So actually we are discussing about graph. So spanning tree is a tree which is constructed from a graph with minimal edges. Okay. So spanning tree is a tree which is constructed from a graph with minimum number of edges. So you know what is a tree? A tree is a graph without cycles, but a graph can have cycles. So given a graph with cycles, we will create a tree, okay, with minimum number of edges, right? Okay, so what is the minimum number of edges required to construct a spanning tree? If the graph contains n vertices, if the graph contains if the graph contains n vertices, then the spanning tree can be constructed by using n minus 1 edges. Okay, so this is the general norm. If a graph contains n vertices, then the spanning tree can be created by using n minus 1 edges. Okay. Minimum you need n minus 1 edges to create a spanning tree. Okay. Right. Or you cannot minimum, it should be n minus 1 edges. Okay. To construct a spanning tree for a graph with n vertex, we need n minus 1 edges. It should not be less than that, it should not be greater than that. Okay. If it is less than that, suppose given a graph, right, you are constructing a spanning tree with n with number of edges which is less than n minus 1, means then that will not be a connected graph. Are you getting? Then that will not be a connected graph. That is, all edges will not be, all vertex will not be connected. Okay. Connected graph means you can reach from any vertex to any other vertex. That may not be possible, right? Otherwise, say you are trying to create a tree, spanning tree from a graph, and the tree contains more than n minus 1 edges, means then that will be a graph, that will not be a tree. Okay, are you getting? Then if you include one more edge beyond n minus 1, then a cycle will be introduced. Okay, so this is the limit to check whether it is a spanning, this is the condition to check whether it is a spanning tree or not. So the point is, to create a spanning tree for a given graph with n vertex, when you create a spanning tree, it will have n minus 1 edges. Okay, it will have n minus 1 edges, right? Okay, so when you create a spanning tree, what happens? We include only some of the edges in the spanning tree. Okay, the graph can have any number of edges. Okay, but in the spanning tree we include only some of the edges. Some of the edges we will exclude from the spanning tree. Okay, so the edges that were included in the spanning tree are called as tree edges, which is represented as T, and the edges which is excluded from the spanning tree are called as non-tree edges, right? So given a graph G, if you construct a spanning tree for that graph G, then it will have T tree edges which are included in the spanning tree, and it will have n non-tree edges which are excluded from the spanning tree. Okay, so T is the set of edges used during the search, and n is a set of remaining edges. Okay, so you may ask why we are using spanning tree like that. So spanning tree is basically used to uh, traverse the tree with what you call, with less number of edges, or with least path, right? Okay, fine. So how to construct a spanning tree? There are two ways to construct a spanning tree. You can construct it either by using a depth first search or by using a breadth first search. Okay, that is, you take a graph and perform depth first search on the graph and keep including the edges as long as there is no cycle. Whenever a cycle is getting created, you stop adding the edge, right? That is, if you are traversing from one vertex to another vertex, look, if you add this edge, will it create a cycle or not? That we should check. If it will not create a cycle, then add that edge. Otherwise, don't add that edge. Okay, like that continue until n minus 1 edges were added, right? So this is the logic. Okay. So the key takeaway point is a spanning tree is a tree which is created from a graph. If the graph contains n vertex, then the spanning tree will have n minus 1 edges. Okay. There are two ways to construct a spanning tree. It can be constructed either by breadth first search or by depth first search. So perform breadth first search or depth first search and keep adding the edges into the spanning tree as long as no cycle is created and as long as the number of edges that are in the tree is less than n minus 1. Okay, right? When it becomes equal to n minus 1, you stop the process. Fine. Here is an example you can see. See, this is a graph. Okay, so these are the different possible spanning tree for this graph. See, this is one spanning tree. Here, if you see, some of the edges were missing. This edge is missing, this edge is missing, and this edge is missing. But this is a spanning tree. This is a spanning tree should be connected. It is connected. You see, from any node you can reach to any other node. From 0 you can go to 1. From 0 you can go to 3. Not directly, but some path is there. From 0 you can go to 2. Like that, from any node we can reach any other node. Okay, and it is connected, right? And there is no cycle. So such a tree is called as a spanning tree. So this is another spanning tree. Here, here different edges are missing. This edge is not there. This edge is not there. And this edge is not there. This is another spanning tree. This, okay. We can also have one more spanning tree. For example, you can have a spanning tree like this: 0. So this is 0. Okay, 0 to 1, 0 to 1, 1 to 2, 1 to 2, 2 to 3. Okay, this is not here, no? Yes, this is also one of the spanning tree. So you see in all this spanning tree, in this graph, how many vertices are there? 1, 2, 3, 4. 4 vertices are there. 4 vertices are there. In this spanning tree, you can check the number of edges. 1, 2, 3. So the number of edges in the spanning tree should be, if the vertex is n, here n is 4, then the number of edges in the spanning tree should be n minus 1, that is it should be 3. So in all the spanning trees you can see the number of edges is 3. So here also it is 3, here it is 3, here it is 3, and here also 1, 2, 3. Right? Okay. Now as we have already discussed, the spanning tree can be created either by performing a depth first search or by performing a breadth first search. If the spanning tree is created by performing a depth first search, then that is called as depth first spanning tree. And if the spanning tree is created by performing a breadth first search, then that is called as breadth first spanning tree. Okay. So, so when you create a spanning tree, it will have n minus 1 edges. Okay. While adding a non-tree edge into a spanning tree, so as we have discussed, when you create after creating a spanning tree, we will add only some of the edges to the spanning tree. Okay, some of the edges will not be added. The edges that will be added will be called as tree edges, and the edges that were not added will be called as non-tree edges. Okay, so so if you add these non-tree edges into the spanning tree, then it will create a cycle. Okay, so if you even add one non-tree edge, it will create a cycle. So here are some examples of spanning tree which is created by using depth first search and a breadth first search. So this is the graph. Okay, on this graph we are performing depth first search. First we are going from 0 to 1. Okay, then we are seeing if you add this edge, will it create a cycle or not in the spanning tree? No, add this edge. Then go from 1 to 3. So if you add this edge, will it create a cycle? No, so add the edge. Then go from 3 to 7. If you add this edge, will it create a cycle? No, so add this edge. Then we are going from 7 to 4. If you add this edge, will it create a cycle? No, so add this edge. Then 4, so from 4, 1 is already visited, so we'll get back to 7, and then 7 to 5. If you add this edge, will it create a cycle? No, so add this edge. Are you getting? Then from 5, 7 is visited, so we have to go to 2. If you add this edge, will it create a cycle? No, so add this edge. From 2, 6 is not visited, 5 is visited, 0 is visited, so you have to come to 6. So if you add this edge, will a cycle be created? No, so add this edge. Now from 6, 7 is there. But if you add this edge, will a cycle be created? Yes. So don't add this edge. Okay. And after adding every edge, you should also count the number of edges. So after adding this edge, you can count 1, 2, 3, 4, 5, 6, 7, and see the number of vertices 8. Okay, number of vertices is 8, number of edges is 7. So this is also one of the criteria to stop the process. So as you have reached, as the number of edges added to the spanning tree has reached, becomes n minus 1, that is becomes equal to the number of vertices minus 1. So you should stop the process. Repeating. So this is the spanning tree created by performing depth first search. Similarly, you can perform breadth first search on it. So first we will add 0. Okay, then from 0 to we are going 1 and 2. So if you add 1, will it create a cycle? No, add 1. So count the number of edges 1. Okay, we need 7 edges. Then if you add this, will it create an, this 2 should be added, right? Will it create an cycle? No, so add this. Now all these things should be added from left to right. So 1, 2, 3. If you add this, will it create a cycle? No, add this. So here number of edge by this time 2, here it is 3. If you add this, will it create a cycle? No, add. Right? Okay. If you add this, will it create a cycle? No, so add. So number of edges added is 1, 2, 3, 4, 5. If you add this, will it create a cycle? No, so add this. Number of edges added is 6. This is not, this is the number of edges. Okay. Then if you add this, will it create a cycle? No. So add this 7. So already 7 edges came. So you have to stop the process, right? But if you go further also, then this edge. If you add this, will it create a cycle? Yes. So you should not add. Okay. So this is how the spanning trees are converted, created or constructed from the given graph. Okay. Fine. So now we are going to discuss something called as minimal cost spanning tree. We are going to discuss something called as minimal cost spanning tree, which has many practical applications. Like for example, in computer networks, or to find a least cost path. Say you might have heard about traveling salesman problem, right? There is a salesman. He want to visit couple of cities. Okay, currently he is in one of the city, right? And what are the cities he has to visit? That can be represented as a graph. Okay, from city A, he can, there is an option that he can go to directly city B or C or D, right? But the cost of reaching B is say 100, cost of reaching C is 200, cost of reaching D is 300. Okay, then D he can go to E. Maybe from C also he can go to E. So like that, the path exists, right? Now, what is the optimal way in which the traveling salesman can travel so that his cost will be minimized? That is one of the classical problem in computer science. Okay, like that there are many problems are there where we have to identify the minimal cost path for a given graph. Okay, for that, if you want to do that, first you have to construct a minimal cost spanning tree, right? So before what we discussed is, just before what we have discussed is spanning tree, right? So spanning tree is the one which is constructed from the graph, and and that is the tree. Okay, if the graph contains n edges, then the spanning tree will have n minus this. If the graph has n vertices, then the spanning tree will have n minus 1 edges. Now minimal cost spanning tree is very much related to spanning tree, but there is a slight difference there. First, I will introduce you graphs with weights. So far, we have not discussed about the concept of weight for the edges. Okay, we have discussed only edges. Edge exists between two vertices. That's what we have discussed. We have not added any weights. Okay, here we are going to discuss graph with weighted edges. Okay, graph with weighted edges. Now you can see this graph. Here for every edge, some weight is added. Weight is mentioned. For every edge, some weight is mentioned. So you may ask, what is this? So this is nothing but the cost of reaching from one vertex to another vertex. So so you can see this edge 0, 5, which means that the cost of moving from 0 to 5 or from 5 to 0. This is an undirected graph, right? So you can say either it is the cost of moving from 0 to 5 or from 5 to 0, the cost involved is 10, right? This cost can be anything. It can be a time, or it can be the expenditure, or it can be the amount of resource that you are going to spend for traveling from one place to another place, okay, right? So like that, the cost can be anything, right? But it represents the what is the cost of reaching from one vertex to another vertex, right? So for example, the cost of reaching from 0 to 1 is 28. The cost of reaching from 1 to 2 is 16. The cost of reaching from 1 to 6 is 14. The cost of reaching from 6 to 4 is 24. The cost of reaching from 5 to 4 is 25. The cost of reaching from 4 to 3 is 22. Like that, so on and so forth, right? Now, what is the concept of minimal spanning tree says in the sense, for this graph, we have to identify a spanning tree. We have to identify a spanning tree such a way that the spanning tree, the cost of the spanning tree should be minimal. Cost, what is the cost means the sum of all the edge cost should be minimal, okay? Finally, if you create a spanning tree for this graph, it will have how many edges? This graph contains 7 vertices, 0 to 6, okay? So if you create a spanning tree for this graph, the spanning tree will have 6 edges, okay? So each of that edge will have a cost. If you add that edge cost, that cost should be minimum, okay? Minimum in the sense that should be the minimum possible spanning tree, okay? There should not be any other spanning tree with cost less than that. There should not be any other spanning tree with cost less than that. Such a spanning tree is called as a minimal cost spanning tree. Are you getting, right? Say for example, let us take I will show you a better let us assume this graph. Let me add some weights here. Say I am calling this 0 to 1 is 1, the weight is 1. 0 to 2 is 2. 2 to 3 is 3. 3 to 1 is 1. Either 3 to 1 or 1 to 3. Okay, 1 to 2 is again 2. Okay, 3 to 0 is 4. Right? Okay, fine. Now let us see what is the, here there are 3 trees are there. Which is the minimal tree? Let us see. We will add one more tree also, as we have discussed. 0, 1, 2, 3. Okay, right. So for this tree, what is the cost? The edge cost of 0, 1 is 1. The edge cost of 0 to 2 is 2. The edge cost of 1 to 3 is 1. So the cost of this spanning tree, the cost of this spanning tree is 2 plus 1, 3, 3 plus 1, 4. Right? If you take this spanning tree, okay, 0 to 1 is 1, 0 to 3 is 4. This is 4. Okay, this is 2. Okay, so this is 4. 0 to 2 is 2. So what is this cost? 4 plus 1, 5, 5 plus 2, 7. Its cost is 7. The cost of this spanning tree is 7. If you take this spanning tree, 0 to 1, 1, 1 to 2, 0 to 2, 2, 2 to 3, 3. Okay, 3 plus 2, 5, 5 plus 1, 6. So the cost of this spanning tree is 6. If you take this spanning tree, 0 to 1 is 1, 1 to 2 is 2, 2 to 3 is 3. Okay, so again it is 3 plus 2, 5, 5 plus 1, 6. Right? I don't know any other spanning tree is possible or not. Okay, but if you see now, now you see which is the minimal cost spanning tree. This is the minimal cost spanning tree. Are you getting? So this is the job of the Kruskal algorithm. Sorry, this is what minimal cost spanning tree algorithm's job is. So minimal cost spanning tree algorithm should find a spanning tree with minimum cost. There should not be any other spanning tree with cost less than that minimal cost spanning tree, right? How to do that? That's what we are going to discuss in the coming slides, right? Okay. So I think you are clear with minimal cost spanning tree. So the cost of a spanning tree of a weighted undirected graph is the sum of the cost of the edges in the spanning tree. The minimum cost spanning tree is a spanning tree of least cost. Okay, so this is the definition. The minimum cost spanning tree is a spanning tree of least cost. So there are three algorithms to to identify the minimal cost spanning tree. These are Kruskal's algorithm, Prim's algorithm, and Solin's algorithm. So in today's session, we'll be discussing about Kruskal's algorithm. Okay. So of course the minimal cost spanning tree will have n minus 1 edges. So we have to select such n minus 1 edges from the weighted graph such a way that these some of these weights should be of minimal cost. Okay. We have to identify such n minus 1 edges from this weighted graph such a way that some of these edge cost should be minimum. Okay, fine. Okay, so first let us discuss about Kruskal's algorithm. So let us discuss this with an example. After that, we'll come to this explanation part. Okay. So this is a given graph. Now, how to find the minimal cost spanning tree for this given graph? So the Kruskal's algorithm, what it says in the sense, first identify all the edges. So if you identify the edges, what are the edges in this graph? 0 to 5 is one edge, 0 to 1 is another edge, 1 to 6 is one edge, 1 to 2 is one edge, 5 to 4 is an edge, 6 to 4 is an edge, 6 to 3 is an edge, 2 to 3 is an edge, 4 to 3 is an edge. Like that, identify all its edge and its cost. And sort the edge in ascending order of cost. And sort the edge in ascending order of cost. Okay. So what is the first edge? 0 to 5. Its cost is what? 10. Second edge 2 to 3. Its cost is 12. Because now these edges were sorted in ascending order. See, the minimal cost edge is 10. It is between 0 to 5. Next higher cost is, next minimal cost is 2 to 3. I mean 12, which is between 2 to 3. Next minimal cost is 14, which is between 1 to 4. Next minimal cost is 16, which is between 1 to 2. Next minimal cost edge is 18, which is between 3 to 6. Next minimal cost edge is 22, which is between 3 to 4. Next minimal cost edge is 24, which is between 4 to 6. Next minimal cost edge is 25, which is between 4 to 5. Next minimal cost edge is 28, which is between 0 to 1. So what we have done here in the sense, we have identified all the edges and we have just sorted it in ascending order. That's it, right? After sorting in ascending order, what should you do? First take the first edge. Okay, first edge you just keep only the vertices, no edges. Okay, here you can see only the vertices are there, edges were there. Now we'll keep adding one by one edges as long as no cycles were created. Already we have sorted in ascending order, so we'll keep adding one by one edges as long as no cycle is added and as long as n minus 1 edges were added. Okay. So first edge you need not check whether it will form a cycle or not. It will not surely form a cycle. So just add the first edge between 0 to 5. Its cost is 10. Second edge between 2 to 3, its cost is 12. So before adding, you see, will it create a cycle? No, it will not create a cycle. Other edges somewhere here. So add this. Okay. So after adding second edge, you got this. Third edge is 1 to 6. Between 1 to 6, the cost is 14. If you add this, will it create a cycle? No. So add this. Cost is 14. Fourth edge between 1 to 2, cost is 16. 1 to 2, if you add this, will it create a cycle? No, it won't create a cycle. So add it. Right? Fifth edge is between 3 to 6. Okay. So fifth edge is between 3 to 6. Now if you add this, you see, will it create a cycle? Yes, it will create a cycle. So don't add. If it will create a cycle, don't add. So 3 to 6 we are not going to add. Don't add. Okay. Next what? 3 to 4. 3 to 4. Okay. So in the previous graph, actually 3 to 4 is, so in this graph you see 3 to 6, if you add, cycle will be created. So don't add. Next is 3 to 4. If you add, will it create a cycle? No, it won't. So add this. Okay. Next 4 to 6. If you add this, will it create a cycle? Yes. So don't add. Don't add this edge. Okay. Next 4 to 5. If you add this, will it create a cycle? No. So add this 4 to 5. Okay, and you count number of edges 1, 2, 3, 4, 5, 6. Number of vertices are 7. So already 6 edges came. So by this time you can stop. Otherwise, if you want to check this also, 0 to 1, cost is 28. If you add this, will it create a cycle? Yes. So don't add. So this is the minimal cost spanning tree. So this is the minimal cost spanning tree which is created. So this is how the Kruskal's algorithm works. So there are different ways of creating minimal cost spanning tree. So this is the idea proposed by Kruskal's. Okay. So the cost of this spanning tree is what? You just add all the edge cost. 10 plus 25 plus 22 plus 12 plus 14 plus 16. Okay, what is that? I think it is 99. So the edge cost of this is 99. Okay. 25 plus 10, 35, 57, 69, 69 plus 30 is 99. Okay, so this is the edge. This is the cost of this spanning tree, right? Okay. Now, how we are going to? I think the logic is clear, right? So the Kruskal's algorithm logic is very simple. First, identify all the edges, sort the edges in ascending order, and add one by one edge to the spanning tree as long as there is no cycle, right? Continue this process until n minus edges, n minus 1 edges were added, right? Okay, right. So this algorithm says whatever we have discussed so far. So the time complexity of Kruskal's algorithm is order of E log E, okay, where E is the number of edges, right? Okay, so how we are going to implement Kruskal's algorithm? So here we have to first, uh, it can also be implemented by using adjacency matrix, okay, or adjacency list, but there is another quite simple way to implement, because here everything is based on the first we have to identify what are the edges and we have to sort the edge in ascending order. Okay, so for that what we can do in the sense, we can define a structure. In C we can define a structure called edge, struct edge, and in this we can include three variables v1, v2 and w. So v1, v2 represents the vertex, the edge, the any edge will connect two vertex, right? What are the two vertices connected by this edge? Okay, that is represented as v1 and v2. Okay, so these are integers. And what is the weight of this edge? So that is w. Okay, so this is how, this is, we can define an edge, we can define a structure edge like this. Okay, and we can create some array of members for this, right? Then you can initialize something like this. For example, ed of 1 dot v1 equal to 1, ed of 1 dot v2 equal to 4, ed of 1 dot w equal to 23. It means there are two vertices v1 and v2. Okay, and there is an edge between v1 and v2, and the weight of this edge is 23. Okay, that is the meaning. Okay, so if you want to specify that there is an edge between two vertices v1 and v2 and its weight is 23, in program we can specify like this through this what you call structure, right? Okay, apart from this, here we will be maintaining an array called parent of. Okay, we can call this array as parent. Okay, for every node, because here one more thing we want to do. See, when we are doing manually, we are saying that you add an edge if the cycle is not there. Directly we are saying, and as a human you can check whether if you add this edge whether a cycle will be created or not. So you can see if there is a cycle, we won't add. If it will not create a cycle, then only we will add. Okay, but when you are going to write a program, how are you going to check which edge will create a cycle and which edge will not create a cycle? First we are going to take edges input from the user and then we are going to sort it. That is quite simple. But after that you should keep adding one by one edge from the minimum cost edge to the spanning tree. When you do that, some of the edge we may not add. For example, 3 to 6 we have not added. Why? Because it created a cycle. 4 to 6 we have not added. Why? Because it created a cycle. So how we are going to recognize that which will create a cycle and which will not create a cycle in the program? For that we are maintaining this parent array. Okay, this parent array I'll explain you how it works with an example. So this array will contain, the size of the array will be equal to the number of vertices. Okay, here the number of vertices is 7. So the size of the array is also 7. That is, it contains that many entries, 0 to 6. And initially all of the values will be filled with -1, right? Which means parent of 0 is -1, parent of 1 is -1, parent of 2 is -1, like that. Every node's parent is initially set as -1. Okay, right? And while progressing using this array, we will identify whether a cycle is created or not. Okay, how that works, that we will check now, right? Okay, see, okay, so let us assume that none of the nodes were added to the spanning tree. Now let us see how this algorithm works, how we are going to implement it. That part we will see, right? See, we are going to take all these. We are going to take all these as inputs. Like how many vertices of the node we will take as an input, right? Then we will ask the user how many edges. That also will take how many edges in the graph. That also will take as an input. Here 9 edges are there. All these edges will take as input from the user. User can give it in any order. Then we will sort all those edges and we will keep it. And we will set this parent array for every vertex as -1. Okay. Now we will take one by one vertex, and what we do in the sense, first we take the first I mean we take one by one edge. First we take the first edge. Okay. Which vertices it connects? It connects vertex 0 and vertex 5. Okay. So we check what is parent of 0. What is parent of 0? -1. If it is -1, it will just return that vertex number itself. So when you check parent of 0, it will return 0. Right? Then we check, so this edge we are taking. So we check what is the parent of 0, and then we check what is parent of 5. What is parent of 5? That is also -1. If it is -1, it will just return that vertex number. What is that vertex number? 5. So when you check 0 here, when you check 0, when you check for vertex 0, it returns 0. When you check for vertex 5, it returns 5. Okay. So then we check whether 0 is equal to 5 or not. Whatever returned, both the things are equal or not. It is not equal. It is not equal. If it is not equal, then that edge will be added in the graph, in the tree. Then that edge will be added in the tree. Okay. So the first edge that we will be adding is this edge. This edge will be added in the tree. Right? I am drawing here. This edge. Assume all other edges were not added. So if both the values are not equal, then we add an edge. Okay. Right. Not only adding the edge, then we will also make that parent of 5 as 0. You can do either way. Either you can say parent of 0 as 5, or you can say parent of 5 as 0. Because it's an undirected edge, right? There is no direction. Okay. So let us say that we are making parent of 5 as 0. So this -1 will become 0, which means parent of 5 is 0, node 0. Parent of vertex 0 is node 0, right? So when we do, first you have to take that edge, you have to take an edge, check that vertex in this array. If it is -1, it will return that vertex number itself. Similarly for 5 also we are checking, if it is -1, it will return that number itself. As both the numbers returned were not equal, that edge should be added in the graph. It means if you add it, it won't create a cycle. Okay. Then we will update its parent here. Now the parent of 5 will be updated to 0. Okay. Similarly do that for the next edge. 2 to 3. 2 to 3. So vertex 2. Check what is the parent of vertex 2? -1. Which means it will return 2 itself. 2. Right. Now 3. What is the parent of 3? -1. Which means it will return 3 itself. Is 2 is equal to 3? No, 2 is not equal to 3. So this edge can be added. The edge between 2 to 3 can be added. So add this edge. Add this edge. Okay, no, because if you add this, it won't create a cycle. That is the meaning. So add this edge. And then what we do? Set its parent to 2. That is, make parent of 3 equal to 2. So parent of 3 will become now 2. Okay, right. Now take the third edge. What is that? 1 to 6. So check parent of 1. Parent of 1 is minus 1, so it will just return 1. Okay. Then check parent of 6. Parent of 6 is also minus 1, so it will just return 6. Is 1 is equal to 6? No, it's not equal. 1 is not equal to 6. So what should you do? You just add that edge to the tree. It won't create a cycle. So 1 to 6, that edge we are adding. Okay, 1 to 6, that edge we are adding, and set that 6, the parent of 6 is 1. So here we change the parent of 6 is 1. Okay, fine. Next, take the next edge, 1 to 2, this edge. Okay, now you check what is 1. 1's parent is minus 1, so it will return 1 itself, right? And what is 6? You see, 6 parent is 1. Okay, if it is not minus 1, this is the first time we are encountering where there is not minus 1. When 6 parent is not minus 1, what is 6 parent? 1. So you go to first location. What is 1's parent? Minus 1. What is 1's parent? Minus 1. So now it will return 1. Are you getting? It will return 1. You getting the point? So now 1 has also returned 1. 6 is also returning 1, because 6 parent is 1 and 1's parent is minus 1. Minus 1 will be never returned. In that case, that parent value will be returned. I mean, that vertex value will be returned, which is 1. So is 1 is equal to 1? Yes, 1 is equal to 1. It means if you add this edge, it will create an, what you call, it will sorry, we are discussing which 1 to 2 we have discussed or not? Yes, 1 to 2. So 1 is 1's parent is, we have to discuss 1 to 2, right? First, 1's parent is what? Minus 1, so it will return 1. 2's parent is what? Minus 1, so it will return 2. So is 1 is equal to 2? No, 1 is not equal to 2. So you can add this edge, 1 to 2 can be added, right? And you change this parent. 2's parent will be 1. 2's parent will be 1. Okay. After that we come to 3 to 6. Now you see what is 3's parent. Now you see what is 3's parent. Okay. 3's parent is what? 3's parent is 2. This is the time we are encountering not minus 1. Okay. So you 3's parent is 2. So you check what is 2's parent. 2's parent is 1. Then check what is 1's parent. Minus 1. Okay. So when you check for 3's parent, it will return 1. When you check for 3's parent, it will return 1. Now check what is 6's parent. Parent of 6. Parent of 6 is 1. Again 1's parent is minus 1. So it will return 1. Okay. For 3's parent also you got 1. For 6's parent also you got 1. Is 1 is equal to 1? Yes. So it means we should not add this edge, because if you add this edge, it will create a cycle. So we won't add this edge, right? We won't add this edge, and we will not update anything. Okay, we will not update anything here. Only if you add this edge, we will update, right? Next, what edge is there? 3 to 4. Okay, so this edge we have not added. 3 to 4. Now you see in this array, what is 3's parent? 3's parent is 2. 2's parent is 1. 1's parent 2's parent is 1. 1's parent is minus 1. So it will return 1, right? Now what is 4's parent? 4's parent is minus 1. So it will return 4. So is 1 is equal to 4? No, 1 is not equal to 4. So we can add this edge. Okay, which edge? 3 to 4. So this edge can be added. This edge can be added. And also we can set that 4's parent is 3. So we will change this. We will make as 4's parent as what? 3. Okay, fine. Right? Okay. Also you should keep adding the number of edges. How many edges we have added so far? 1, 2, 3, 4, 5. 5 edges we have added. Totally how many vertices? 7 vertices. So we should add only one more edge. Okay, right. So next we will see 4 to 6. 4 to 6. 4. What is 4's parent? 4's parent is 3. 3's parent is 2. 2's parent is 1. 1's parent is minus 1. So 4's parent, when you check, it will return 1. Okay. Then what you have? 6. What is 6's parent? 6. The parent of 6 is 1 and 1's parent is minus 1. So this also returns 1. Is 1 is equal to 1? Yes. So don't add this edge, because if you add this edge it will create a cycle. So this edge we won't add, don't add, right? Okay, so this we are not adding, right? Then check 4 to 5. What is 4 to 5? What is 4's parent? 4's parent is 3, 3's parent is 2, 2's parent is 1, 1's parent is minus 1, so it will return 1 when you check for 4. Okay. Similarly, check for 5. What is 5's parent? 5's parent is 0, 0's parent is minus 1, so this will return 0. Is 1 is equal to 0? No, 1 not equal to 0. So add this edge. 4 to 5 you add. Okay. 4 to 5 add. And also set that 5's parent as 4 or 4's parent 5. Anything you can do. Already here it is made that 5's parent is 0. But here now you can change. You can change 5's parent as 4. Right? Okay. Or otherwise you could have also made 4's parent as 5. Both way it will work. Correctly it will work. Okay. Right? Now you have made 4's parent as 5. Okay. And you have added this edge. This edge we have added. Okay. Now how many edges are there? 6 edges are there. 5 plus 1 equal to 6. Okay. Now you stop the process, because after every time you have to check and you have to stop. Otherwise this algorithm will not work correctly. Here n minus 1 edges we have added. How many vertices are there? 7 vertices. So 6 edges we have added. So at this time you stop. Because if you check for 0 and 1, no, it may not match and it will be added. But that is not correct. But we will not go for checking here. Because after adding every edge, we will check the number of edges. If it becomes equal to what you call n minus 1, we will stop. Right? So this is how the algorithm is going to work. Now let us see the code. Now let us see the code. Okay. So many WSLs are there. I don't know which one. Yeah, this one. Take the graph also. This is also not required. So this is how the Kruskal's algorithm work. First, then we'll come. So nano Kruskal's. This is not there. Kruskal.c. So this is the header files we are using, stdio.h and stdlib.h, and you can see here the we are creating a structure which is named as edges, which contains three members a, b, and w of type integer. So a represents the one vertex and b represents another vertex. So an edge connects two vertex, right? And what is the weight of that edge? That is represented as w, right? And here we are creating an array of edges of 100, and capital V represents number of vertices. Okay. And I edges represents currently how many edges were added into the what you call spanning tree. Currently how many edges were added into the spanning tree. So here I am initializing as 1 instead of 0. You can also initialize with 0, but I am initializing as 1. Okay, we are as if I am assuming that one edge was already added. Okay, right? Then NED represents the number of edges in the uh, number of edges in the graph. Okay, and this parent array, as we have discussed, we have to maintain a parent array. For that, this parent array initially minimum cost is set to 0. Okay, this I edges and NED both are same. Okay, actually I think I am using this NE. I edges I am not using. NE represents number of edges that were currently added to the spanning tree. We are assuming one edge was already added, right? Okay, this is just for counting convenience. I'll tell you why I'm initializing with 1 later, right? Then we are creating an yeah, this is no okay, this is not required here. This is not required here because we are going to create what structure. We need an array of structures for edges, right? So here what we are doing, struct edges ed of 100. Okay, so for this structure edges we are creating an array of size 100. Okay, and also we are creating a variable t for this structure edges. This is for what you call, while sorting we have to swap for that, right? So here is the sort function. We'll come back to this later. And this is the initialize parent function, which will initialize all the parent values to -1. Okay, so here you can see initialize parent. We are declaring a variable I. For I is equal to 0, I less than v. V is the number of vertices, I plus plus. Parent of I is equal to -1. Initially we set the parent of all vertices as -1. Okay, this find logic and this include, I think I'm not using this. I'll delete this. I thought of using. Okay, I'll delete this. So let us start with main function. So here we are declaring some variables I, j, x, y. Okay, first we are asking the user enter the number of vertices in the graph that is stored in v. Okay, and then we are asking the user to enter the number of edges, and that is stored in ned in the graph. Okay, then we are asking the user to enter all the edges and its weight. So edges in the sense, for example, if there is an edge between 0 to 1, okay, if there is an edge between 0 to 5, then the user should enter like this: 0, 5, 10, which means there is an edge between 0 to 5 and its weight is 10. Okay, to represent the edge 1, 1 to 6, so it is understood as either 0 to 5 or 5 to 0, right? 1 to 6, the edge cost is, the weight is 14, so user should represent as 1, 6, 14, which means that there is an edge from the vertex 1 to 6 and the weight is 14. Okay, so that's the meaning, right? So for every, I mean, we know the number of edges that we have taken as input from the user. So we are asking the user to enter the edge and its weight, and that is stored in ed of I. So here I starts with 0. So ed of 0 dot a, ed of 0 dot b, and ed of 0 dot w will have the edge details of the first edge and its weight. Okay, so on and so forth, like that every edge we receive in this ed array. Okay, then we are sorting this ed, because user need not enter this what you call these edges in a sorted way. It will be in any order, then we have to sort it. For that we are calling this sort function. So let us assume that this sort function will sort it. Let us discuss that sort function later. Then initialize parent, which we have discussed already. What it will do in the sense, it will make that parent array as -1 for all the vertex. Okay, here we are just displaying all the edges in the sorted order, right? Then comes the actual logic. Then what we are doing, for I is equal to 0, I less than ned, that is number of edges, I plus plus, we take each edge. Okay, each edge contains what? Starting vertex, ending vertex, and weight. So we take the starting vertex of the what you call starting vertex of the first edge, and we are passing it to the find function. Okay, the find function will check its parent. Are you getting? The find function will check its parent. If the parent is -1, it will return that value itself. Otherwise, it will continue until the parent value becomes -1. Where it becomes -1, that particular node value it will return. Okay. So the find function, here is the logic, whatever we have discussed there. So it takes one integer p, which is nothing but the vertex number. So we check while parent of p not equal to -1. Suppose if parent of p is -1, then it won't enter into the loop and it will just return p. That's it. If parent of p is -1, then what we do is p is equal to parent of p. Then p becomes parent of p. Then again we check whether its parent is -1 or not. Like that we continue until it becomes -1. When it becomes -1, then we return that p. Right? I think you are able to connect it. Right? say for example here, if 0 and 5, initially when you see 0 is what is 0, it is parent of 0 is -1, so it will return 0, right? Or if you take this case, 3 comma 4, now after updating parent of 3, if you check parent of 3 is 2, so that we are using that while loop, okay? And then parent of 2 is what? 1. Parent of 1 is -1, so it will return 1. That is, when you pause 3 to find, it will return actually 1. After uh, coming this many, when you are coming for this particular edge, initially for this edge, 3 also will return -1. Are you getting? So that is what that function does. Okay, I hope you are understanding. So like that we are checking for each edge there are two vertex. For every vertex we are checking find of ed of I dot a, and similarly we are finding ed of I dot b. So whatever the, for first vertex whatever we got, that it is stored in x. For second vertex whatever we got, that is stored in y. Then what we check after that, we check whether x is equal to y or not. Every time we compare, 0 returns what, 5 returns what, is it equal or not? If it is not equal, that edge should be added to the spanning tree. So we are checking if x is not equal to y. If x is not equal to y, then that edge should be added to the spanning tree, and also you have to make that parent of y is equal to x. So we make that parent of y is equal to x, and we are adding to spanning tree. Here adding to spanning tree means we are just displaying it. We are just displaying that this is one of the edge in the spanning tree, like that we are displaying. Okay, right? So what we are saying, percentage d, percentage d, in the sense this is the first edge. Okay, now you can understand why I gave ne as 1. Initially I gave ne 1, no. So now here if I give percentage d, it will give 1. It is post increment, right? So it will display first edge. First edge is what? Percentage d comma percentage d. Which edge? It is ed of I dot a comma ed of I dot b. And what is its weight? Ed of I dot w. Okay. So far, how many edges were added to the spanning tree and what is its cost? That will be updated in minimal cost. Initially, minimal cost is set as 0. So now here we are doing minimal cost plus equal to ed of I dot w. Right? So that is what we are doing here. So after adding every edge, so if based on this condition we will add an edge or we may not add an edge. Okay. So after adding every edge, we check whether ne is the number of edges in the tree, spanning tree. Okay, whether ne is equal to v. See, why you may ask why it is not equal to v minus 1. It should be v minus 1, right? Why we are checking v? It should be v minus 1 if you start ne with 0, but I am starting ne with 1. Are you getting my point? If you are confused with this, then here you can make ne as 0 instead of what you call 1, you can make it as 0. Okay, as I am starting ne as 0, here I am checking whether ne is equal to v or not, because it is post increment. After adding one edge, this will become 2. Okay, so after adding 6 edge, it will become 7. Are you getting my point? After adding, in this particular graph, if you see there are 7 vertices, so you have to add 6 edges. After adding 6 edges, it will become 7. So that we are checking whether n is equal to v. So 7 equal to 7, then it will break, right? Okay, so this is the core logic, and finally we display the minimal cost. This is the minimal cost, so and so. Okay, so let us execute this. So gcc c hyphen o slash asking the number of edges, number of vertices. So let me, where is the ppt? So number of vertices is 7, right? 7. Number of edges is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, one more edge is here, it's not visible. Actually, it is 7, 9. So number of edges are 9. What are the edges? Enter the edge and its weight, one by one edge. So first, so we need not add this in this order. From this graph we can add. Okay, first edge is what, between 0 and, okay, what is its weight? 10. Second edge is between 0 and 1. What is its weight? 28. Third edge is between, say, 1 to 6. Okay, yeah, 1 to 6. What is its weight? 14. Okay, then what is its weight? 16. Okay, right. 0 to 5 added, 0 to 1 added, 1 to 6, 1 to 2. Then 5. 5 to 4. 5 to 4. 5 to 4. The weight is 25. Okay, 6 to 4. 6 to 4. Oh, 5 to 4 the weight is 25, right? 6 to 4 the weight is 24. 6 to 3 the weight is 18. Then 4 to 3 the weight is 22. Then 2 to 3 the weight is 12. Okay, first it sorts the in ascending order: 0 to 5, 10, 2 to 3, 1 to 6, 1 to 2, 6 to 3, 6 to 3 or 3 to 6, either way, right? Okay, 3 to 4 or 4 to 3 both are same. 6 to 4 or 4 to 6 both are same. 4 to 5 or 5 to 4 both are same. 0 to 1 which is of highest cost. Okay, then you see what are the edges it is adding. Let us take the minimal spanning tree. So it is adding 0 to 5, its cost is 10. Then it is adding 2 to 3, its cost is 12. Then it is adding 1 to 6, its cost is 14. Then it is adding 1 to 2, whose cost is 16. Then it is adding, see, 4 to 3, it is not adding 3 to 6. Already it is sorted, but it is not adding 3 to 6 or 6 to 3. Okay, right? Okay, then it is adding 5 to 4. Okay, again, see, 3 after adding 3 to 4, 3 to 6 is missing, right? It is not adding 4 to 6, it is adding 5 to 4. Okay, and it is not adding 0 to 1. The last one is not added because we are checking whether n minus 1 edges are there. If there are n minus 1 edges, then we come out, and the minimum cost is 99. Okay, so you can check out with some other graph also, undirected graph also, it should work, right? So that's it about Kruskal's algorithm. So let us stop here. Thank you.